Okay, so let's start. Thank you for the joining us today for the Silicon Valley Deep Specification meetup online this time. So quick agenda. We'll talk for 5 minutes briefly about some administrative stuff, announcement, and etc. And then we proceed to the main talk about the formal verification of computer programs by Nika. And after the presentation, we have about half an hour, up to half an hour of question answers. So it's been a while since we met, so I would like to introduce myself. My name is Vadim Zaliva, and I volunteered to step in as an organizer of this meetup. It's get bounced on the meetup.com. I got notification, and I'll try to do my best. I would like to thank the previous host, Christopher, who created this meetup back in 2016. I just checked; it's impressive, and hopefully it will go on for longer. So we'll try to do some changes compared to the previous format. Previously, we've been going through the software foundations and some other exercises and textbook. And I would like to try for a change a little bit more kind of a talk presentation format, where we'll be presenting different we will be inviting different speakers to talk about different developments in the field, present different techniques and projects, etc., in the software verification, and relate to the deep specification kind of approach. We will try to maintain the balance between the academic and industrial material. So this area is kind of in the crossover from the academia into the kind of into the industry, and we certainly, like as a Silicon Valley meetup, we would like to keep it a little bit practical, a little bit grounded to something you might want to use. We would like to use in the industry, but at the same time, we would need to be aware of the interesting stuff coming from the academia. So we'll have a mix of the speakers from the both academia and industry. We have some ideas who to invite, but if you would like to talk yourself, or you know somebody who would like to talk, please reach out to me and with ideas for the presenters and talks, a proposal for the talks. Right now we're limited to the virtual format. Eventually we'll hopefully return back to the physical. Maybe we'll keep the virtual aspect as well. We'll do both. We'll see how it goes, but for virtual for now. And taking advantage of the virtual time, we're also trying different time slot. Usually we meet in the evening and afternoon, this meetup, and this time I'm trying to do this lunchtime meetup. So I'm not sure how it works for everybody. If it's convenient, feel free to leave the comments at the meetup. What do you think about this time? Or if you have strong preference towards the evening meetings after 5 p.m. or lunchtime works as well. You can chew your food and listen for some interesting talks at the same time. As to the venue, I think we lost the previous venue which we used before. We lost access to it, and we will be looking for the new venue where we will be performing the in-person meetings, the physical meetings after it opens up. I don't have anything lined up yet. So if your company would like to host it, you're in the Bay Area, or your university, or your organization, please reach out. I will be glad to hear if somebody wants to host. And always feedback and suggestion is very welcome. I would like to hear how we're doing and what works, what's not. On each list of meetup, I would like to do a community announcement session. So people reaching out, and if you want to announce your project or something relevant, feel free to reach out before the meetup, and I will be glad to announce it here. We'll see. Maybe we can do like 1 minute verbal, visual announcements. So, but for now, let's just send me the material. So, a couple of announcements for this time. So right now you might be aware that the PLDI conference is going on. It's Programming Language Design Implementation. There is a lot of talks there and the discussions related to the software verification and the correctness of the software program relevant to the topics of this meetup. It's one of the leading conferences in this field. It's streamed live, so you can join on the YouTube and listen to the presentations, or you can listen for them later. So that's going on right now until this Friday, and unfortunately we already almost done, but you still can watch it. And also there is a Haskell Love conference. They reached out and asked to do the community announcement here. It will be an online conference in July 31st, and they still open for the call for papers, CFP. So if you want to submit something for the conference to be presented there, you still have a little bit of time left. And we're not affiliated with them. I'm not affiliated with them, but I checked and they have fantastic lineup of the keynote speakers like Simon Pettit-Jones, Connell Elliott, John Wigley. So it's I will be attending, so I hope you might as well. So if you have any announcement for the next meetup, send them out prior to the meeting, and I will be glad to announce. And we're about to proceed to the next talk, which I'm about to announce. If anybody have any quick administrative questions or comments, now it's the time to talk. Please go ahead. All right, I assume we're on the same page now. So today's talk is formal verification of computer programs and primer. So speaker is Nika Pona. So she had her master's degrees in computational logic from a Technology University of Vienna, where she wrote a thesis on proof theory and development of SAT solver for many varied logics. And then she worked at the University of Barcelona on the formal verification of legal software and research of proof theory with probability logics. And she's currently working as a proof engineer at Digamma.ai on formal verification of software written in C language. Her academic interests include formal methods, type theory, and foundations of mathematics. And by the way, this talk will be recorded, and if you missed it, I will publish the link at the meetup.com afterwards, so you can revisit it. So without further ado, I pass the stand to Nika. Nika.
Hi everyone, thanks for joining me and thanks for doing this at lunch, because for me it's 10 p.m. And do you hear me all right, Vadim? Can you tell me if everything is fine? Yeah, okay, great. Okay, so today I will going to tell you about formal verification of computer programs. So I will do a sort of introduction. First, I will do a sort of introduction to what is formal verification, how you usually do it. But mostly I will concentrate on how you verify imperative programs. So I hope everyone will learn something new from today. Okay, so first of all, just a quick intro for those of you who may not know what is formal verification. So basically it's a method to have high assurance that the code we wrote works as intended. So you can do tests, but also instead you can do formal verification, which means that you produce a formal proof of correctness that your code works as intended. So how do you typically do this? So first of all, you write the formal specification in some formal language. So usually it's some kind of logical language. And this specification is unambiguous and well-defined. And so you have to distinguish it from informal specification. So informal specification, it can be ISO standard or comment in code, which can be ambiguous, it's written in English. But here we choose a formal language and write the specification. Okay, then what we have is a model of our program that we want to verify and its behavior. So we define in the same formal language, we define the semantics of this program. And then finally, we can prove that this semantics, that this behavior matches the specification. So today I will talk about formal verification of imperative programs in Coq Proof Assistant. So it's one of many proof assistants out there, and it's only one of the formal methods. Okay, so first of all, I will tell you about an example that we worked on in Digamma.ai. So we are working on verifying a compiler from ASN1 language to C, and we wanted to test our approach of verifying imperative programs. So we only had informal specification, which was written in comments. So this function string to imax, it was taking a string. So it was taking a pointer to a string and an end position and was parsing it to a number. And also it was returning the last parsed character. And it was writing it into some pointers. So let me show you the code of this function. So let's concentrate a bit on this example because we will use it a lot. So as I said, it takes to pointer, it takes beginning pointer and end pointer, and then we're writing the result in some other pointer. So this function, it converts string to number, but it also does, it has 5 error messages. So for instance, if the pointers you gave didn't make sense, so the end was actually before the beginning, then you get an error message, invalid input. Then you read, otherwise you read the string, and if there is a sign, you write the sign. And if there is nothing else except the sign, there is another error that you expect more. If all of that goes through, then you actually do the conversion from string to the number. Okay, and the important thing here to note is that you check for boundaries. So you want to prevent the overflow mistakes. So here you check the boundaries. And if they don't go through, you get an error range mistake. And if everything is okay, then you just do the typical conversion. You multiply your value and you add the converted digit. And there is case distinction for plus and minus, because for minus case, the upper boundary, it will be different than for the positive case. Okay, so you do all this conversion and you return okay if everything goes through. So semantically, it's pretty simple function, but since we are working in C, we need to do the overflow checks. Also, we're writing in the memory. So there are many things that should be verified, and there are many potential mistakes in such kind of code. And I want to emphasize that this is a function taken from the existing code base that has been tested. It has been used for 15 years, and we decided to try and verify if it works correctly. Okay, so what we found? We actually found 3 bugs while working on this function. So the first thing, and surprisingly, it was a problem with an overflow. Also, they did the checks there. Still, there was a problem that on some inputs, there was a wrong number. So for instance, if your input, sometimes if you went below the the maximum negative integer, you would get an okay result, although you clearly went out of the range. And here it's example for 8-bit architecture. So the maximum number should be minus 128. Okay. So how did we discover this bug? Well, when you formally verify a function, you have to cover all cases. So when you do the proof, you realize that something doesn't match, and you actually see the counterexample. So in the proof, you find the counterexample, and then you fix it, and only then you can prove that it works correctly. Okay, so this bug was fixed. How is it fixed? Let me go here. So the bug was introduced here. It was in this place. So here, when we reach the last possible value, we go to the next character, to the next location, and if we find a character, well, it means we're either out of range, or we read a non-digit. Okay, so this was fixed. Okay, so this is the important part of the code. So this was the fix, and we found the bug in the fixed version. So here, look precisely. So what we do, as you remember from the informal specifications, that you have to write in the end pointer, you have to store the location where you stopped in the conversion. Okay, so here you store it, and then you do the check. Then you do the check on the digit. Okay, so the bugs that we found, we also found it in the proof, and we found the counterexample, and it's quite difficult to reproduce in reality. But here's the idea. So imagine that our minimal integer is something like this, and we're trying to read something smaller. Okay, so ideally we should have error range error on this input. So this is our number, and once we and the end pointer where we want to write down the location, is located somewhere later in the memory massive. So once we finish the location, we just write the end after there, and we output error range. So this is good. This is how it's supposed to work. But imagine a more complicated scenario where your end pointer actually points within the string that you are reading. So in this fix, as you remember, you were first storing the location where you stop and then reading. So in this situation, what can happen is that you store the location and you change the data that you're going to read in the next step, so you get the extra data. So this is one of the bugs we also discovered here. Well, and it can be treated either as a bug or an implicit precondition, because actually we don't want to accept this kind of pointers, and we implicitly state that the pointer should not point into the same place where the string is. Okay, and the last bug or a feature, we don't know yet, is that after we fix these two bugs, we finish the proof, but then we realized that it has some maybe unintended behavior. For instance, for input, which is just a character which is not digit, it actually returns value 0, but a correct message. And this can be intended by developers or not, but we wrote our specification, reading the comment and also looking at the code, trying to understand what developers wanted. And so in the end, this just shows you that you have to be really careful when writing the specification, because you may as well prove that the function works correctly, but your specification may be wrong. And this is a kind of questions that formal verification cannot answer for you. Okay, so something that we learned from this example. Well, first, that formal verification is indeed quite useful, because in this very simple function, auxiliary functions that we took at random, we found already some problems. And the problems we found, they can be actually treated with formal verification, because the first problem was with pointer arithmetic and integer arithmetic. It was with integer arithmetic. And when you do formal verification, you have a strict mathematical model of machine arithmetic, so it's actually quite easy to do the proofs, and it's a very good infrastructure to do such proofs. And you will expose all such bugs. You will have to prove, you will have to expose the bugs while proving. And the second problem was related to the memory. And these problems are quite difficult to test, and they're not really obvious. And in formal verification of imperative programs, you have actually also a rigorous memory model of C, and you have actually good reasoning tools for speaking about such problems. It's called separation logic, and I will talk about it. Okay, well, and our third issue showed us that the formal verification is only as good as your specification. Okay. So this was just an example to motivate you, to show that formal verification actually is very needed, and it is actually more fine-tuned, so to say, than testing. Okay, so now I will go to tell you a bit about COC, and this is a tool we used to do the verification. We chose COC because it gives you a formal language in which you can formalize your specification, in which you can have a model of your programs, and in which you can do proofs, everything in one tool. So it's based on calculus of inductive constructions, so it's a very rich type theory. Yes, and now I will tell you a bit about COC, and if you have questions about COC, you can ask them after I finish. So what is COC generally? So it's an environment in which you can define functions, you can define predicates. So basically it's like any other functional language, but a bit more restrictive. Also, you can state mathematical theorems and specifications, and then you can develop formal proofs of these theorems. And then these proofs are checked by the kernel of Coq, and this is actually the part that you have to trust. But this kernel is said to be quite small, and it's developed and checked regularly. And then once you did these proofs, what you can do, you can compile the programs that you wrote. You can compile them to a camel Haskell, and then you can use them in some real-world scenarios. So one of the typical formal verification projects is when you write your software in Coq. So you write a functional program, you prove some properties about it, and then you extract it to a camel Haskell, and then you can compile it and use it. Okay, so now I will talk a bit more about Coq, and this is mostly for people who know nothing about Coq and formal verification. So I took a very simple example of factorial. So imagine you have a specification on paper of factorial. So in Coq, you can actually practically mirror this definition. So there is a keyword fixed point, which is used for recursive function. So basically for factorial, if it's 0, it goes to 1. If it's successor, well, you do what the mathematical definitions tell you. Okay, so this is the definition of factorial, and it's at the same time it's a specification and a function, because it's a pretty simple function. You can just inspect it and see that it corresponds to what you wrote on paper. But for more complicated programs, you may want to use a more logical approach, so to say. So I rewrote the definition we had in a more logical way. So you can also write definition of factorial like an inductive definition. So you say that factorial for 0 is 1, and then if factorial something, then blah, blah, blah. So it's a more logical way of stating that. In Coq, this corresponds to inductive keyword. So basically, this defines a relation factorial between natural numbers. You can also look at it as an axioms that tell you what is factorial. And let me give you another example about this inductive definition, which may be not familiar for many of you. So another simple example is sorting. So you can write also inductive definition as before. So basically, you declaratively describe what a sorted list is. So you want an empty list to be sorted, you want the singleton to be sorted, and then once you have a list which is non-empty, which is sorted, you just prepend an element to it which is smaller than that element. Okay. So this is a very simple definition, and then you can take your favorite sorting algorithm and prove that it actually corresponds to this kind of definition. Okay, and there is an alternative definition of specification. Writing a specification is more of an art than a science. So basically, you try to write it so that it's readable, understandable, it's easy to check if it is correct, and also which makes your proofs easier. Okay, so let's go back to the factorial. So imagine that we wrote a different factorial function. So here is the recursive function. And now it's maybe not as obvious that it is correct. So we actually want to check if it computes the same answer as the factorial we defined before. And in Coq, what you do, you state, and there is a keyword for that, theorem. You state a theorem. And you just say that for all natural numbers, our new factorial gives exactly the same answer as our functional specification. Also, you can use the relations that we defined to state exactly the same thing. And I will very quickly show you how Coq looks like. So here are our definitions. So this is a factorial definition. So this is the theorem that we stated that our factorial is correct, and I took the easy factorial function, and we just want to show that this relation and these functions are the same. So you state the theorem, and then you enter the proof environment. Okay, and here you can see. You cannot see. Can you see? Sorry.
No.
Sorry. Thanks for saying that. I need to present it. Okay. Window. Okay. I'm really sorry for that. Now you can see the screen.
Yes.
Okay, so now, I was just showing how Coq looks like and what you can do there. So now we want to prove that our factorial function is correct. And in Coq, you do this by using tactics. So here is in violet color. So for instance, you want to prove this by induction. Okay. And then you can see on the right that you have different goals now that you want to prove. And you can prove them by using the axioms. So you use the first axiom of our specification. Okay. And then you go to the next case, and then you just unfold the definition. And then you apply the different axiom, and then by assumption, you're done. And then you have the QED, and you can only accept the proof and have QED if it's the correct proof. So now what we have actually a verified proof of this very simple theorem. Okay, so that was a very quick intro to Coq. Okay, so what's after that? So we had some functional programs. We proved that they're correct. And now we can use Coq's extraction mechanism and have a factorial program in Occam and Haskell, which we prove this correct, and we can use it. Okay, so this is how the functional verification usually works. Okay, but what if we want to verify code written not in Coq, but in some imperative language? So now I will tell you about this, and it gets much more complicated. Okay, because here what we had was that we had our program written in Coq already, and it was a function. Since it's a functional language, it was a function, so it's already a mathematical object about which we can do proofs. So this was quite straightforward. But now if we have, for instance, a C program, we can still state specification about it and do proofs in Coq, but we need to somehow represent the C program, the C function, in Coq. So this means that we need some model of C syntax and its semantics. And we don't have to do this from scratch. It has already been done in the project called CompCert. CompCert is a verified compiler for C. And it's written in Coq, and it's proved to work correctly. And it has been tested also for all kinds of bugs, and apparently it has it doesn't have middle-end bugs compared to other compilers. And in this project, what they did, they actually defined C syntax and C semantics in Coq. So we used it. So we used it in our project. What we did, we took the C code, the existing C code, we parsed it using CompCert, using the so-called C-Lite generator. Then we wrote a functional specification in Coq, and we used CompCert's memory model and integer representation for that. And then we proved properties about the generated AST using the semantics defined in CompCert. And what we actually used was not the C language and C semantics, it was C-Lite language and C-Lite semantics. So C-Lite is just a slightly restricted version of C. And from our practice, so here's a list of unsupported features. From our practice, some of the features which are not supported are quite useful. For instance, that structs and unions cannot be passed by value, that type qualifiers are erased at parsing. But some of the things you can overcome them, and you can still reason about functions that use this kind of stuff. Okay, so let's go back to the factorial. So here is a C program that we want to to verify. So the specification is the same. Now we just want to prove that this function corresponds to that specification. So this is how it's represented in Coq. It looks a bit scary, but it's just an abstract syntax tree. And let me go quickly over the elements. So this is a syntax tree in which in leaves it has expressions. And then in the nodes, you have the statements that connect different expressions and different statements. So for instance, you have such expressions as constants, and E stands for expression. So for instance, you have a constant integer expression, and this is its value, so it's 0, and you have a type which is integer. Then the expressions can be binary operations. So here it's binary operation, add, and you add 0 to 1. Yeah. You also have temporary variables, and you have the type as well, and you have the references, etc. And then statements, they start with S. So for instance, you can set identifier to some constant. Then you have a return statement, so it can return some value. And then sequence, well, is just a sequence of expressions. So it takes 2 arguments, 1 and 2. And then there are loops, so while, which takes an expression and a statement. Okay, so this is how you read this kind of stuff. And well, we can go back and look at it. So now maybe it's a bit more clear what it means. So basically, it's just difficult to look at representation of the code that we had, and it's also annotated with types. Okay. So now we have the syntax, but now we want to understand, we want to reason about it. And how do you do it? You do it using operational semantics. So operational semantics, it's a mathematical model of language execution. So it is basically an interpreter. And we use big step operational semantics from CompSert. So let me tell you a bit about operational semantics. So the idea is quite simple. So since you have a tree, you start with the nodes which are expressions, and you also parse them, and to constants you assign some primitive values, which can be integers or booleans, or they can be values taken from local environments. And then you compositionally compute the expressions. So if it's addition, you also map that to plus on integers, etc. And then when you have expressions, you want to give meaning to statements. And meaning of statement is the result of their execution. Okay, so the execution of a statement, it produces an outcome. So it can be as a break, or it can be normal execution, or it can be return. And what a statement does, it can update local environment, and it can update memory. Okay, so you have these 2 main elements, and there are different semantics, expressions and statements. And I will show you examples now, so it's a bit easier to understand. As for some parts of the semantics, I will talk about integers. So in CompSert, you have precise model of machine integers, and it is represented as a bounded arbitrary precision integer. So you have an integer which is in Coq Z, so it's just an infinite type, and then you have a bound on it. So the modulus is just the biggest integer you have. And this is the type on which you can reason, and there are many tactics that allow you to reason on this kind of types in Coq and do proofs. Another thing that you need to define semantics is memory model. So memory model is a specification of memory states and operations over memory. In CompSert, memory states are accessed by addresses, which are just a pair of an identifier and byte offset. And each address is also associated with permissions. So it can be read permission, write permission, all permissions, or no permissions. And the semantics of this memory is defined by 4 main operations. So which is load, so you read memory at a given address, you store some memory at a given address, allocate memory, or invalidate the memory block. So you define this kind of operations, and then you have some properties of these operations. So load can succeed only if you're reading memory which have reading permissions, for instance, and that the value returned by load belongs to the type of the memory quantity accessed, etc. So you have some theorems that you prove about these operations that should hold of a meaningful memory model. So finally, here are some examples of everything I just said. So for instance, take an expression, which is a constant integer 0 of type integer. Okay. So you evaluate it in a context of local environment, and the local environment is just a map from variables to values. You also evaluate it in a context of some memory, but since it's an expression, it doesn't actually matter. If it's a constant expression, so it doesn't matter which local environment and memory. So actually it evaluates to 0 and to the same local environment and memory. Okay, so this is the simplest example. Then you have a statement which is set as to 0. So you evaluate it in local environment, in memory, and what happens? Well, naturally, local environment is changed. So this means that in the local environment LE, you assign to S 0. The memory shouldn't change, and the outcome is normal. So basically, you interpreted this syntax to this kind of value. And then the statement, for instance, return. So you want to return that S. You also evaluate it in local environment and memory. It doesn't change them, but the outcome now is a return. So this is how the operational semantics looks like. And now, using this semantics, we can actually state correctness. Okay, so now we'll be quantifying not only over natural numbers as we did before. So we were proving that for all natural numbers, factorial n is actually correct. So we are quantifying, we're saying that for all local environments, for all memory, if the input is assigned n, then our factorial function, and this corresponds just to our abstract syntax tree, then it terminates, and this exists, just says that, well, we are ending up with some local environment and the same memory, and the outcome, which is return, and you return the factorial n, and this factorial n is actually the specifications that we wrote in Coq before. So in this way, we are connecting the C language and our functional specifications that we wrote in Coq. Okay, so now I will go back to our previous example and tell you how we actually specified and proved the string to Emacs function. And we used the semantics that I showed you before, but on top of it, we used separation logic, because it's a bit easier to reason in separation logic. So you can do this using verified software toolchain, and here I give the link to it so you can check it out. So what is separation logic? So separation logic triple, PCQ, it's a triple where the P and Q are propositions, and C is a statement of AST that I showed you before. And the intended meaning of this triple is that given the precondition P, the execution of the function C terminates, and after it terminates, the postcondition Q is true. And a separation logic is defined by rules for such valid triples. And I will not define separation logic for you here, but I will just give some examples so you understand what kind of rules there can be. So the first one is an assignment rule. So if you start with a precondition P and you have an assignment statement, then the precondition P will also hold, but you have to substitute A for X in P. So this is an axiom of the separation logic here. Then if you have a skip statement, which in C-Lite, it's just a statement that does nothing. So if the precondition is true before, it will be true after. And then for more complex statement, for instance, sequence. So if you have a sequence statement and you execute it from the precondition P and get Q, it means that for some P prime, the first statement goes from P to P prime, and the second statement goes from P prime to Q. So this is a kind of rules, and then we are doing proofs in this logic. Okay, so how do we state correctness of our function using separation logic? Is actually very similar to what I showed you about operational semantics. So we also state that our function, which will be C here, that the triple PCQ holds, and that in precondition we just state where the input is mapped, and in the post condition we will say that the C returns the value according to the executable spec. And I'll show you an example now. I just have to add something that we didn't see before, that in factorial, for instance, the memory changes here, and we also make some statements about memory in the precondition and in the post condition. So we do this using special predicates. Here it's an error, but later it will be written differently, sorry for that. So it means that at address P there is a value V. And this kind of predicate, it is special because you can combine it with other predicates, not only using conjunction, disjunction, application, but also a special conjunction, which is called separating conjunction. And when you combine two spatial predicates, it means that each conjunct is true on a separate subheap of the memory. So, for instance, when we talked about the second bug that we uncovered, we actually want this kind of precondition. We want to say that the pointer which points to string is separate from the pointer which points to the end pointer. Also, in the precondition, you want to relate the C types to abstract types of calc. Okay, so I will show you now a full example. In the rest of the talk, I will just show you more details of how we did it, how we did the proof, and how the spec looks like. So the first thing, we wrote functional specification. So we did it as for factorial. And also, well, we keep it simple here. This is just a function which converts a string, and here we represent it as a list of bytes. So it reads a string, and then it outputs you a number, or it outputs you none if it cannot convert it. So if the string is empty, then you get none. If you just read a singleton, which is not a digit, which is a sign, you also output none. And then if you read plus or minus, then you calculate correspondingly. And then the loop is quite straightforward. If you read a digit, well, then you just convert it as usually. If not, just return. So this is a functional specification, and it's pretty simple to look at it and to see if it worked correctly or not. And you can notice that it doesn't talk about machine integers. It uses abstract types. It uses booleans and list of bytes. So this is just a functional program. Okay, we can also specify it using relational specification, as I showed you before, which is maybe simpler, but for this particular function, it's pretty much the same. So here instead of a function, you write a relation. So you're saying that if you have some strings that you converted and you're reading something which is not a digit, well, then the whole thing will be accepted by this function, and it will be accepted by the extra data axiom. So I will not stop on this. Okay, so we have our functional specification, and that's what we're using. We can prove it correct with respect to relational specification, just to make sure that we actually wrote the correct specification. And then what we do, in order to make the proof, we can move in two directions. So we have our functional specification, but remember that it was I'll go back to it. Remember that it used the type set, and also that it didn't have any error messages, so it was returning none. We can still use it in the proof, and we can say that for all numbers which are smaller than which are within the bounds of maximal integers, our C function works correctly, and then we can map error messages to none here. But it's a bit messy, so instead what we do, we introduce within this spec error messages and everything we need for the proof. So this is pretty much the same function. What it does, it gives you error messages where was none in some cases. But also it introduces a bounds check that you had in the function, so you don't want to go out of range. So if you go, you give an error here. And also what you do, you output error message, you output value, but also you output I, which is an index. This is the place where we stopped. So this is something that we want to write in the memory. And again, what we can do here, we can prove that this functional specification is, with some condition, is equivalent to the functional specification. And we are going to use this spec in our proof. Okay, so this was preliminary work to state actually the specification. So this is how the VST specification looks like. So first we have a with clause, which tells you what kind of variables you're using. So here we have our string, ls, which is list of bytes, and we have all our pointers, which is a value in compsert. Then you also state what kind of types are the parameters. And this is actually the predicate, the precondition. So the prop stands for proposition. Here you add, here you actually add some propositions which are true before executing the function. So you want to have some readable permissions, the code shares in VST. You also want to have some writable permissions, and we'll use them below. And one of the things you want to have in the precondition is that the list that you have is actually not too big, because remember that here we're using abstract types, abstract mathematical types, so it can be arbitrarily large. So we are saying that if we add to string the length of the string, we are not going out of range of the permitted pointers. Then in the local case, you connect your identifiers, which are taken from parsing your C function, and these abstract values. So you're saying that that variable str should be interpreted like this value. So you connect, here is where you connect your actual code written in C to your model in Coq. And then SEP stands for separation logic. Here where you state memory predicate or the special predicate, as I showed you before. And here I don't use the arrow, I decided to make it more realistic. So in VST, you have this predicate which is called code data at. So here you have first element is a permission. So here it's a read permission. And we're saying that at this pointer, which is related to the str pointer variable, we have our string, ls, and its type is array of length of ls, and it's a read permission to that. Then we also had a double pointer in our function where we store the end address, so it points to some pointer with it has to be write permission here. And then we had intp pointer where we're actually writing the result, which was I think integer type, and you have a write permission. So this is all the preconditions we have to execute this function. And of course, you should try to make them as minimal as possible. So this is the precondition, and this is the post condition. So if we had that precondition and we executed the function, so this is what we want to get. So our output type will be integer. So it will be just an error message coded as integer. And now we want to use our abstract specification. And our specification gave us some result, some value, and the index. And in proposition, we don't add anything new. Nothing new is true after executing the function. And as for variables, we are only interested in the return value. So redtemp stands for return value. So what we are stating here is that after executing the function, we return the value, which is a value that our functional specification gives. And then also we wrote something in the memory, and something stayed the same. So here we state first things that shouldn't change. So we really don't want the string to be modified in this function, because it may be passed later, etc. So this depends on the specification of the function. So we say that this doesn't change, so the string still the str still points to the string, and then memory did change depending on in which case we were. So if our result was OK or extra data, it means that in the intp pointer we write the value v, and it's still with the write permission. But if it was anything else, we actually did not modify the intp pointer, so we state that. And another case, we were also supposed to store the index where we stopped. And it depended also in which case we were. So if we compared the input pointers, and the end pointer was actually smaller or equal to str, then it didn't change. So we have the same thing we had in the precondition. So here are the things from these are the things from the preconditions that in some branches of the executions, they don't change. Otherwise, we store the index at ndp. Okay, so this is the post condition. And again, I want to emphasize this is where the correctness statement happens. So we are stating that the return of our C function is actually the same as the return of our functional specification. And what we write in memory is actually corresponding to what our functional specification gives. And the proof of the separation logic triple is done using so-called forward simulation. So to prove the triple, you start by assuming the precondition, and then you sequentially execute statements of the function. And each statement generates a postcondition that follows from its execution. And then after executing the last statement of C, you prove that the postcondition holds. And you do this proof by using the rules of the separation logic. And VST provides some automatization of the steps. But one still has to manually provide some intermediate postconditions for if statements, for instance, or for loop invariants where semantics is more complicated and it cannot be automated, you have to provide loop invariants to do the proof. Okay, so to conclude, Coq can be used to prove correctness not only of functional programs, but also imperative programs. But you need some additional work to embed C-syntax and semantics in Coq. And the take-home message is that if you want to prove a C function correct in Coq, one of the methods to do it is to write a formal specification of the function in Coq, then take comcert and generate a C-lite AST, and then prove that the resulting AST evaluates to correct values on all valid inputs, and you can use either operational semantics or separation logic. Since I have some minutes left, I will go back to operational semantics. So here we had factorial, but we could have stated the correctness theorem also for our string to max function. So what we'd have to do is to say that in the local environment, some values are mapped to what we want for the parameters. We would also have to make some assumptions about where the memory is mapped. And then we would have to also modify here the local environment and the memory and the return. But the statement would be pretty much similar. As you can see, the statements are quite similar to what we have in the separation logic, because the idea is that you assume something about local environments, about memory, then you execute in that local environment and memory your function, and then you get some return. The difference is within the proof. Here in operational semantics, you actually you do an ordinary mathematical proof about the semantics. So you just execute the function. But in separation logic, so you can do it by induction, for instance. But in separation logic proof, the whole proof you do in using separation logic proof. So you do like any typical logic proof. Okay, so let's go back to conclusion. So I think this is everything I wanted to tell you, and I think there will be some questions. Thank you for listening.
Thank you, Nika. And now it's time we can ask any questions you want. So if anybody have questions, please go ahead. Actually, there was one question in chat I noticed. Unfortunately, the person who asked already left, but he asked if we capturing the fact that C integers have finite precision.
Capturing the fact that C integers have finite precision. Well, yes, the idea is that in the formal model of integers and arithmetic, you want to capture exactly how the integers of C are behaving, and they are different from the abstract types that you have, which are arbitrary precision with arbitrary precision. So, yeah.
Okay. Okay, we see more questions in the chat.
Okay, so my understanding is that separation logic is an extension of Hoare logic. Simply put, what are the differences? Addition. Okay, so the Hoare logic is a historical logic, so the stuff that I showed you about precondition and postconditions, it was invented a long time ago. The separation logic, it just adds rules for memory. So I think before you had just rules that didn't deal with memory, for instance, or with concurrency. So it's just a more sophisticated separation logic, but it's the same principles that are lying behind there. So basically what you're modifying is the propositions that you are accepting, so the P and Q. You modifying what kind of logical assertion you can have there, and you add more rules. But any kind of rule you add, it still will be Hoare separation logic.
Yeah, just to extend on that, so it's based on the core logic and just extension of the core logic, and it just adds some additional connectives, and which allow you to reason about the memory and especially things like separate, not overlapping memory blocks and changes. All right. Yeah, I think the get take out of this is just, this is a state of the art how things are done, improving the imperative programs in C right now, and as you can see, it's not an easy task yet. So there are things which could be improved here, hopefully, and people are working in that direction. I hope. So right now it's somehow a laborious process, but it's could be done, and people doing that.
So, are there any more questions? Don't be shy. If you didn't understand anything, it's a perfect time to ask. We have some time.
All right. Okay, so looks like no more questions. We'll post a video of this presentation, and please feel free to reach out with additional follow-up questions, either in comments or emailing Nika or me. Just reach us anyway. We will be glad to answer. And we would like to hear more about the ideas about future talks and speakers. Thanks, Nika.
Okay, thank you very much. Thanks, everyone.
Thanks. Bye.